When we hear the word graph, we typically think of the Euclidean coordinate system and figures that we have worked with for many years. We know that these graphs are representations of the relationship between x and y and occasionally z, a concrete connection from the independent to the unknown. But what else can graphs be used for? To answer this question, we must travel back nearly 300 years to Königsberg, Prussia, known today as Kaliningrad, Russia. Consider the following problem. Two islands that sat in the Pragal River that ran through the city. The western island was known as the Knifoff, and the eastern island was known as the Loms. Knifoff had 4 bridges connecting it to the rest of the city, and Loms had 2. There was one single middle bridge that connected the 2 islands. This design posed a question to the people of Königsberg. Was it possible for a traveler to cross every bridge once and only once in a single trip? Go ahead and try to solve this problem. No matter what route the traveler will attempt, there is no way that every bridge can be crossed once and only once in a single path. This much was apparent to the people of Königsberg, but no one had an exact answer as to why. No one, of course, until Leonhard Euler came along. Euler was a Swiss mathematician that set the basis for what is known today as graph theory. His proof of the lack of a solution for this knife-off bridge problem revolutionized how mathematicians considered these types of issues. But before we get to the actual proof, we must first set some definitions. Professor Christine Kinsey, a topologist at Canisius College in New York, defines a graph as a finite non-empty set V of vertices, or points, along with a set E of edges between pairs of vertices. A loop is an edge from a vertex to itself. Since the only information that matters from the problem is the number of bridges and islands, we can reimagine the map as a much more abstract graph, as Euler did. Island Knifoff is vertex A, the south part of the city is vertex B, the north part of the city is vertex C, and Island Loms is vertex D. As you can see, all of the bridges are represented as edges between these vertices. A path in this graph is defined as a string of edges where the ending point of one edge in the path is the starting point of the next edge, and where each edge can only be used at most once. Each vertex in the graph, also known as a node, has a certain number of edges connecting to it. Euler recognized this as the degree of the node. A loop to a node also adds 2 to the degree, as it technically touches the node twice. Since you can only cross a bridge once in the knife-off problem, it makes sense that the degree of each node should go down by 1 as you take a bridge to it and use a bridge to leave it. Therefore, as you travel through the path, it makes sense that the degree of each node you cross goes down by 2. The only nodes that don't follow this rule are the starting and ending nodes, which only go down by 1. This means that for a path to be a Euler path, or one that touches every edge, there are 2 possible cases that must be met. Each node in the graph must have an even degree, or there must be exactly 2 nodes in the path that have an odd degree, our starting and ending nodes. Since all of the nodes in the knife-off problem have odd degrees, it makes sense that neither of these cases are fulfilled, and it is impossible to find a solution. This mathematical proof set Euler as the father of graph theory and cemented his position in history as a mathematical figure. Professor M.J. Fortin, a professor of ecology at the University of Toronto, stresses the importance of using spatial graph theory in biology and ecology. For example, the food chain can be represented as nodes and directed edges for the organisms in the direction of consumption. Lakes and water movement can be represented using graph theory as well. Plant ecologists can use graph theory to show the proximity of plant species to one another, and there are many other uses for graph theory in ecology.
Next, we'll be going over Gaussian graphs. These graphs are derived from the observations of Carl Gauss from around 1830. They were proved about 100 years later by Julius Nagy. A Gaussian graph is a planar map that can be drawn by a single closed curve that goes straight at each vertex. Similarly, it has been found that sand drawings or Sona drawings made in various cultures around the world can be described as Gaussian graphs. These drawings are made in the same way so that no pieces of the graph touch without crossing and all points are only crossed by two pieces.
The women in Tamil Nadu, a state in South India, for example, create geometric designs out of rice flowers at the entrances of their homes. These designs, known as kolam, can be represented as graphs like the knife-off bridge problem.
Trees are another type of graph. A tree is a connected graph with no cycles, or you can call it acyclic. A cycle occurs when you join the vertices of a graph from the first until nth vertices, then join the nth to the first. This creates what looks like a polygon. These examples here are all cyclic graphs. If we take these points here, connect each vertice, and now we connect the last to this first one, we have a cyclic graph. Here's one last example. As you can probably tell, this is not a cycle graph. However, it does have subgraphs that are cycles, such as here and here. This makes it cyclic, and therefore cannot be a tree, because trees, as we said, are acyclic. From this, we can understand another aspect of trees. The number of edges in a graph is equal to the number of vertices minus 1. In this cyclic graph, we can see that it has 3 vertices and 3 edges. But in trees, we're not making this last connection. If we draw these points here and connect them like this, we have a tree. So an example of a tree that you may be familiar with is a family tree. These are a part of what is called a rooted tree, which is one vertex that's been designated as the root, and every other vertex comes away from it. Every tree doesn't have to be like this, but rooted ones do. So if we have root R, and these next vertices are A and B, and then from A we have, say, X, then Y, then from B we have C and D, you can see a family tree coming into place. And if we count the number of vertices, 7, then the number of edges, 6, you can see that this is a tree. It is connected, there are no cycles, and the amount of edges is 1 less than the amount of vertices.
So as a final review, problems like the knife-off bridge can be represented as a graph and solved through graph theory by analyzing the paths between points on the graph.
Gaussian graphs are a closed curve in which no pieces touch without crossing and are only crossed by 2 lines. Lastly, trees, similarly, can be represented by a series of dots and lines, which when connected fully are called cyclic graphs.
That's all we have.
Covered for graph theory,
And have a nice day.